This is 7.1, radicals and rational exponents. We're going to be determining the nth roots of numbers and evaluating radical expressions. Use the rules of exponents to evaluate or simplify expressions with rational exponents, and evaluate radical functions and find the domains of radical functions. So roots and radicals, the definition of an nth root. Now, we say nth root, nth can be any number. We could say square root, fifth root, plug in any number for n, you can find the root of it. So a and b are real numbers, and let n be an integer, and it's got to be 2 or more. Okay, so if you're taking the nth root, the square root, the cube root, the fourth root, the fifth root, those are all numbers that are greater than or equal to 2. This may or may not mean anything to you, but so I'm going to use the example of 36 equals 6 squared. So what that means is 36 is your A, 6 is your B. Okay, and we know that 6 squared is equal to 36. So this works in an opposite direction. If our power is 2, then we can square root, we can find the second root of 36. And that would give us 6. So over here, I just did that. The square root of 36 is 6. Now, the square root of 36 with a negative out in front means you're going to have a negative in front of your square root of 36, which is 6, so that makes us a negative 6. Down here, though, is there a number that when I multiply it by itself, it gives me negative 4? Like in problem A, what number times itself gives you 36? Well, 6 times 6 is 36. Okay, in other words, what number multiplies by itself to get me negative 4? Well, it can't be a 2 and a 2, because a 2 and a 2 would give me a positive 4. It can't be a negative 2 and a negative 2, because that would give me a positive 4 as well. So there is actually no square root of negative 4. Down here, now we're taking the cube root of 8. So we have to figure out what times what equals 8, and that's going to be 2 times 2 times 2. In other words, it's 2 cubed. So our answer here to this problem is just 2. Down here, what times what times what will give me negative 8? And the answer is negative 2. Now, principal nth root. We don't pay a whole lot of mind to principal nth root, but I just want to mention that principal nth root means that it has the same sign. So let's just go through and determine A, B, C, D, or E, or multiple answers, which one has a principal nth root. So if you look at the number inside your radical and the answer, if they have the same sign, whether they're both positive or both negative, it has a principal nth root. So the square root of 36 has a principal nth root. In here, though, our answer was a negative 6, and the sign under our radical was a positive, so that would not be a principal nth root. Here we have a negative, and there was no answer, so that would not have a principal nth root. Over here, we have an 8 and a positive 2. They're both positive, so that's a principal nth root. A negative 8 and a negative 2, that would also be a principal nth root. The important thing about this box is the 2 vocab words, index and radicand. The index is whatever root you're taking it. So sometimes, mostly it's squared, but over here, the index was a 3. And then we have radicand. Radicand is the number underneath the radical. So the radicand in this problem was 8. The radicand in this problem was 36. Now let's classify some perfect nth roots. So we either have a perfect square, or we have a perfect cube, or we have neither. Okay, so we're trying to figure out, is 81 a perfect square, a perfect cube, or neither? Well, 81 I know is the same as 9 squared. 9 times 9, hey, that's a perfect square. We could check to see if it's a perfect cube. So what times what times what gives me 81, and there is no number. Negative 125. Check to see if it's a perfect square. Is there any number when you multiply it by itself, it gives you negative 125? And immediately I know that's false because nothing times itself would give me a negative answer. So it's definitely not a perfect square. However, it is a perfect cube because negative 5 cubed gives me negative 125. Down here, 64. I know that 8 squared will give me 64, so this is a perfect square. But I also know, or type in my calculator, that 4 cubed would give me 64. So this is also a perfect cube. 32. Is there any number when I multiply by itself it gives me 32, or is there any number when I multiply it by itself 3 times it'll give me 32? And the answer is no, it's neither a perfect square nor a perfect cube. However, 2 to the 5th would give me 32, so it is a perfect fifth. Down here I have a negative 64. So what times what will give me a negative 64? And again, nothing, because nothing times itself will give me a negative. So I need to check for a perfect cube. I know it's got to be negative, and from above I know it's 4. Inverse operations and evaluating rational expressions. So a square and a square root are inverse operations of each other. Remember we said that the square root of 36 is the same as 6 squared. Okay, well, they work opposites. I'm sorry. 36 is equal to 6 squared. And when we square root this side, our square and our square root cancel. So we get 6 is equal to the square root of 36. Inverse operations cancel each other out. So look what I have going on here. I have the square root of 4, but I am squaring it. There's a couple different ways you can look at this. You can look inside your parentheses and solve that first. So the square root of 4 I know is 2. But remember, I'm squaring that, and I get 4. So I have the same answer that I would normally get if I just had realized that the square root and the square cancel, and I'm left with a 4. Down here, I have a cubed root and a cube. Those are going to cancel, but if you didn't realize that, we could solve it the long way. So let's simplify our in our parentheses first. The cube root of 27 would be 3, because 3 times 3 times 3 is 27. And now I'm cubing that answer, so I get 27. Down here, it works the same way with fourth root being raised to the 4th power, but let's simplify it one step at a time. So the 4th root of 16 would be 2, and I'm raising that to the 4th. 2 to the 4th is 16. And you kind of get the idea. It's going to work for the 5th power, but in case you want more practice simplifying our parentheses, we get negative 3, because negative 3 times itself 5 times would get me negative 243. Now I'm raising this to the 5th power. Negative 3 to the 5th power, negative 243. Down here, again, shortcut method is to say, hey, a cube and a cube root cancel each other out, so I'm left with a 4. A cube root and a cube cancel each other out, I'm left with a negative 2. A square and a square root cancel, and a square root and a square cancel. Now, I have some inverse properties. The main one that I want you to look at is down here. If n is even, then notice what I have going on here. I have an even index and an even power. So which one of our examples has that? Well, H does. I have an even index, right? It's a square root. When the 2 is not written, that means it's a square, and an even power, just like in this example here. So it says I need to take the absolute value of my radicand. So my radicand is negative 3. I need to take the absolute value of it, and my answer is 3. This is the important one. The 1 and 2 just say exactly what we did here. It says that we can cancel if n is odd. So if you have like a cube root raised to the 3rd power, those are going to cancel and give you a. You're probably wondering, you're thinking, hey, in problem G, I have an even power and an even index. So why didn't we take the absolute value there? Well, we absolutely should have took the absolute value of 7. I just didn't write it because the absolute value of a positive 7 is 7 itself. So don't forget that one. Make sure you take the absolute value of whatever is under your radical. Okay, we have 2 different forms that we can write rational exponents in. We have a radical form and then a rational exponent form. So in this example, we're given the radical form, and this is split up into 4 different problems. So I need to write this radical form in a rational exponent form. So let's look at the definition of rational exponents. Same thing going on. If I'm taking an nth root of radicand A, then I can write this root as a radicand with a rational exponent. Remember, rational just means fraction. So I'm writing my root as a fractional exponent. Notice in my exponent, I have 1 over n. N is the index in your root. So your denominator always is your index. Where did this 1 numerator come from? Well, it actually came because there's a power of 1 on A. So the power is your numerator. And the index is your denominator. And that's important. And it gives a better description down here. So let's say we're starting with the rational exponent form, a raised to the m over n. Well, I can write this in radical form. I can write it as a root. So remember, our numerator is our power. So we have a to the m power, and our denominator is our index. So we're taking the nth root of a and raising it to the m power. Let's try to do that over here. I have the square root of 36. That's in radical form. So my index here is 2, and the power on 36 is 1. So I can rewrite this as 36 to the 1/2 power. 1, since it's my power, is my numerator, 2, since it's my index, is my denominator. That also equals 6. These mean the same thing. Two different forms, but they both give me 6. Let's look down here. Now we're given the rational exponent form, and we have to write it in the radical form. So I'm given my number 256, and it's raised to a fraction exponent. So what number, 3 or 4, is my root? What is the index? Well, I come over here and I see that the index is the denominator. So I'm taking the 4th root of 256, and 3, since it's my numerator, it's the power. So I'm taking that to the 3rd power. That would also equal 64 if I simplified it. And I messed up on my lines here. Let me fix this. Kind of skinny, gotta write small. All right, I have u to the 1/4. So I'm taking u to the 4th root, because 4 is my denominator, and 1 is the power that I'm raising it to. Now I don't necessarily have to write to the power of 1, so I can just write the 4th root of u. Down here, I'm taking the cube root of 27 squared. Okay, so this 3, does it become my numerator or my denominator? Well, since it's the index, it's going to be my denominator. 2 is my power, so it's my numerator. So I have 27 to the 2/3. Now both of those would actually equal 9. Okay, evaluating. So we have A, B, C, D, E, F problems that we need to do here. 8 to the 4/3. There's a couple different ways. Now when I look at this, I see a lot of different ways to solve this. One way to think about it is doing what we just did. Taking our rational exponent and writing it as an index and a power. So my denominator, 3, means I'm taking the cube root of 8 to the 4th power. Now you can write the 4 underneath your radical or outside your radical. Either one is fine. I am going to write it outside of my radical, and you'll see why in just a second. So like we said earlier, we can simplify inside our parentheses. So the cube root of 8 is 2, because 2 times 2 times 2 would give me 8. So now I'm taking 2 to the 4th power, and I get 16. That's one way of doing it. And it's probably the quickest way. But there are others. So let's take a look at B. A lot going on here, a lot of different things. We haven't talked about it yet in this lesson, but we have in the last chapter. We talked about power rules. Okay, so I'm taking 4 to the 2nd power, but I'm also taking that to the 3/2 power. So I have a power times, or a power raised to another power. We'll talk about it on the next slide, a power to a power. So that's one way of doing it. I'm going to do it a different way. I'm going to simplify inside my parentheses. So 4 squared is 16. That means I'm taking 16 to the 3/2 power. Well, now I'm ready to put this into radical form. So 2 is my index, and 3 is my power. I'm going to simplify in my parentheses. The square root of 16 is 4. 4 to the third power is going to give me 64. C. Okay, also from last chapter, remember we had a rule that said if our exponent was negative, we could move it to the denominator and it changes positive. So that's one way of doing it, but there is another way. I'm going to go ahead and do it this way since I already have it written down. So think back to last chapter. If our exponent is negative, remember this is negative 3/2, I can change it positive by moving it to the denominator. The 25 goes with it. They're attached to each other. So I have 1 in the numerator. And I need to write 25 to the 3/2 in radical form. So I'm taking the square root of 25 to the power of 3. Simplifying the square root of 25, I get 5. 5 to the power of 3 means 125. So my final answer is 1 over 125. Moving on to D. Again, a few different ways you could do this. There isn't one set way, and that's the beautiful thing about math. One of our rules of exponents said that if you're taking this exponent to a fraction, remember it goes to both the top and the bottom. It's attached to the 64 and the 2/3 is attached to the 125. So I'm going to go ahead and do it that way. But like I said, multiple ways. Because I have a number raised to a fraction exponent, I can write it in radical form. I'm taking the cube root, so my denominator is my index, of 64 raised to the second power. That's my numerator. Down here, I'm taking the cube root of 125 raised to the second power. And I'm going to simplify. The cube root of 64 is 4. The cube root of 125 is 5. Square them, and you get 16 over 25. I mentioned there are multiple ways of doing this. You could have simplified this 64 over 125 first, and then gave the 2/3 to both of those items. All right, problem E. I'm going to write this in radical form. So this negative is not in parentheses. It's not with the 16. It's just hanging out in front, kind of third wheeling. So I'm going to put the negative out in front. My denominator gets to be my radical. So I'm taking the square root, but I don't have to write the 2, of 16 to the first power. I don't have to write the power of 1. So now when I simplify this, I'm taking the square root of 16. Remember, there's a negative out in front, and the square root of 16 is 4. If the problem would be different if I had parentheses around the negative with the 16. Because what that means is, hey, now you're taking the square root of negative 16 to the first power. And we can't take a square root of a negative number, so that would not have existed. So parentheses matter, especially when we're dealing with negatives. And the last one, here it is. I did not even notice. So we're taking the square root of negative 16 to the first power. And like I said, there is no real number that is the square root of negative 16. I'm so smart and ahead of myself that I just put that one in there. I knew I was going to be thinking about it. All right, rules of exponents, and this is what we've kind of already talked about in previous chapters. Remember, we have product and quotient rules. So notice how all of these have the same base number or letter. So whether you're dealing with x's or they're both y's or maybe they're both 2's, they have to have the same base. If they're the same base and you're multiplying, you add the powers. Okay, so such as over here, 4 to the 1/2 and 4 to the 1/3. Same base, so my base stays the same. I add my fractions, 1/2 plus 1/3 is 5/6. Remember, when you add fractions, what do you have to have? Oh yeah, common denominator. So this is not equivalent to 2/5. Wrong. It is equivalent to 5/6, however, because you need that common denominator of 6. Okay, so same base, and this time we are dividing. When we're dividing, we're going to subtract our powers. The top power, R, minus the bottom power, S. And this gives a good example over here. Base is the same, it's x. I have an x squared and an x to the 1/2. So that means I'm taking 2 minus the 1/2 in my exponent, and I get x to the 3/2. Power rules. So those were products and quotient when your bases are being multiplied and divided. Power rules means a power outside of either a product, a quotient, or another power. So a times b to the power of r means this r goes to everything in your parentheses. It attaches to your a and it attaches to your b. Well, now we're back to up here. Except, why can we not add these r's? Because we don't have the same bases. We have an a and a b. That's as simplified as we can get. So a good example is over here. We have 2 times an x, all raised to the 1/2. So this 1/2 goes to the 2, and it goes to the x. But we cannot add the 1/2s because our bases are not the same. A 2 and an x are not the same. Okay, so power to a power. One base of an a raised to the r, but it's also being raised to the s. Remember, power to a power, we can multiply those exponents. So x cubed raised to the 1/2 means you can take x to the 3 times 1/2. And when you do that, you get x to the 3/2. Multiply fractions straight across. Okay, we have a quotient here. They're being divided, but it's raised to the power of r, which means r goes to everything in your parentheses, the top and the bottom. Just a refresher on 0 and negative exponents. Anything to the 0 power is 1. If we have a negative exponent, we can make it positive by taking it to the denominator. And if we have a negative exponent on a fraction, we can make it positive by flipping our fraction. So keep these 8 summary rules of exponents in mind when doing these problems. Let's use rational exponents to rewrite and simplify each expression. Well, what's going on here? Well, before we can even talk about rules of exponents, we need to make sure that we have exponents and not square roots or fourth roots in this matter. So how can I write this, right? Because this is one term, it's being multiplied by x here. How can I write this set of parentheses as just x to a power? Well, I have my x out in front, okay? And in my parentheses, didn't we say that our index could be your denominator and your power can be your numerator? So now I have x to a fractional exponent and I have x to the first out in front. So these are two things with the same base being multiplied. So I'm looking at my first product rule. I'm going to add my exponents. So this is x to the 1 plus 3/4. 1 plus 3/4 is 1 3/4, otherwise known as 7/4. Part B, same thing. I need to change my x's so that they are only in powers and not in nth roots. So in the numerator, I have x to the 2/3, and in the denominator, I have x to the 3/2. I'm going to be looking at my second rule over here because I am dividing. They have the same base of x. So I'm going to subtract my exponents. My top exponent, 2/3, minus my bottom exponent, 3/2. 2/3 minus 3/2, to spare you the time of typing it into your calculator, is negative 5/6. Oh, now I have a negative exponent. So which rule does that fall under? Oh, that's rule 7. To change it positive, I need to move it to the denominator. Remember, x goes with it, and all you do is change it positive. Okay, here, everything under our radical, the x squared times y, is being cube rooted. So I have x squared y. Remember, this is to the power of 1. So 1 is my numerator, and my index is my denominator. Now I have two things inside my parentheses, such as in part 3, being raised to a power of 1/3. So what I'm going to do is make sure that the x squared gets the power of 1/3 and the y gets the power of 1/3. Well, I can simplify this further because look at our x squared to the 1/3. That's a power on a power. That's rule 4. A power to another power means I multiply them. So a 2 times a 1/3 is 2/3. So I have x to the 2/3, y to the 1/3. I cannot combine any further because my x and my y are not the same base. Okay, let's go to problem number D. I have the square root of the cube root of x. So let's work outside to inside. I'm sorry, let's work inside to outside. So underneath our radical, I have a cube root of x to the first power. So I can write this as x to the 1/3. Now let's handle the outside radical. Remember, it's a squared when that 2 isn't there. So what you're doing is you're taking your x to the 1/3, right? And it's going to get a power of 1/2. The 2 came from the index. The 1 came from the power on the x to the 1/3. Again, I have a power raised to another power, so I'm going to be multiplying them. And I get x to the 1/6. Ooh, a lot going on down here. Let's just handle it one at a time. My numerator is always in, or already in, a rational exponent, so I don't have to deal with that right away. I'm going to look at my denominator. And it's a cube root, and this 2x minus 1 is to the power of 1. So I'm taking 2x minus 1 to the 1/3 power now. Okay, so I have one thing in the top raised to a power and one thing in the bottom raised to a power. Sorry, that should be a minus in there. So what it looks like to me is rule 2. Right, one thing in the top raised to a power, one thing in the bottom raised to a power. So I'm going to be subtracting my exponents here. Because they have the same base, just like a and a, now a is 2x minus 1. So I'm keeping my base same, just like here, a. I'm taking r minus s. So my top number is 4/3, and I'm subtracting it with 1/3. These have a common denominator, so I can just subtract 4 minus 1, and I get 3. Oops. So I have 2x minus 1 to the 3/3. Well, 3/3 simplifies to 1, so it's 2x to the first power, which I don't have to write to the first power because it's just itself. So my final answer is 2x minus 1. Radical functions now. It wants us to evaluate this function when x equals 4. So remember, a function means that you could plug in an x value into the function and solve for it. So that's what we're going to do here. F of 4, that means 4 is what we're plugging in. We're taking the cube root of 4 minus 31. So that's the cube root of negative 25. I'm sorry, 27. The cube root of negative 27. We can take a cube root of a negative number, and that's going to give us negative 3. Negative 3 times itself 3 times would give me negative 27. Over here, I'm again going to let x equals 4. So my function is g. G of 4 is the square root of 16 minus 3 times 4. Well, 3 times 4 is 12. 16 minus 12 is 4. The square root of 4 would give me 2. So evaluating is all about plugging in and simplifying. So let's come down here and practice some more. If at any point you want to pause the video and see if you get the correct answer, please do so. I would be more than thrilled if you did that. F is 0. So all you do is plug in 0 for x. Simplify. 2 times 0 is 0. 0 minus 1 is negative 1. What number times itself 3 times gives you negative 1? And the answer is negative 1. Over here, f is 62. Sorry, negative 62. So again, I'm going to plug in negative 62 for x. Simplify. 2 times negative 62 is going to give me negative 124. Minus 1 is negative 125. The cube root of negative 125 is negative 5. Over here, negative 13, so same idea. You get the cube root of negative 27, which equals negative 3. And last one, cube root of 63. Um, 126 minus 1, 125. Cube root of 125 is simply 5. All right, hopefully you got those all correct. Let's move on. Finding the domain of a radical function. Now, we've touched on this before, but underneath our radical, it cannot be negative if n is even. Okay, so cannot be negative if n is even. Remember, n is our index. So that means if we're taking the square root, or the fourth root, or the sixth root, underneath our radical cannot be a negative number. It has to be positive. So it can be 0, but it can't be negative 1 or negative 0.1. All non-negative numbers. But if n is odd, so our index is an odd number, such as the cube root, the fifth root, the seventh root. If n is odd, then it can be anything, all real numbers. So the only time that we have to be weary is when we're taking the square root or the fourth root or any even root. So let's look down here. The fifth root of x. Well, if the root is odd, it can be anything. It could be all real numbers. So the domain here, you could say all real numbers. If you don't like the all real numbers symbol, just write it out. All real numbers. The other notation you might see is from negative infinity to positive infinity. X can be anything underneath that radical, is basically what this notation is saying. Down here, I'm taking 3 times the square root of x. So my index is not 3, it's a 2. It's the square root when it's not written. So what we need to decide now is everything under my radical has to be bigger than 0 or equal to 0. It can't be less than 0 because anything less than 0 is negative. We cannot have a negative underneath a square root. So we have to make sure that x is, since it's under the radical, is bigger than or equal to 0. This is my domain. X must be greater than or equal to 0. Can't be anything less than 0 because then it would be negative, and that's not good. All right, down here, again, I'm taking a square root, so my index, my n, is even. So everything under my radical has to be bigger than or equal to 0. So 2x minus 1 has to be greater than or equal to 0. But now, it wants the domain, so we're trying to figure out what values of x can I plug in. So this inequality sentence here doesn't tell me anything. I want to know what can I plug in for x and it be okay. So I need to solve this. I'm going to add 1. Then divide by 2. And now I get x is greater than or equal to 1/2. That means something to me. That's saying, hey, if you want to plug something into this function, it's got to be 1/2 or more. Can't be anything less. Try plugging in like 0.25. If you plug in 0.25, you're going to get a negative underneath this radical, and you can't take a square root of a negative. Okay, so our domain here, x is greater than or equal to 1/2. All right, if you have any questions, please don't hesitate to ask or look in the book. I'd be happy to help you with any of your homework problems or clarify something from the notes.